Okay, hi everyone. Sorry for the delay. Just waiting for a couple of people to come in and join us. Just a short sound check. If you can hear what I'm saying, just leave it in the comments below. Okay, today we're going to be continuing and completing. Okay, we're going to be completing our first subtopic. Okay, for this chapter, which is gravitation. Okay, and I hope that you have your module with you. Uh, the paper 3 module that I gave to you all. Cause yeah, this one. Okay, so that if in case you want to write any notes or anything, okay, you can write it in there lah. Okay, but basically we're going to finish up this subtopic today. So let's get started. So today we are going to be looking at uh, this. Okay, sorry. Okay, so we're going to be looking at the third part, okay, of this first subtopic in this chapter. So the first subtopic, as I said before, this is Newton's universal law of gravitation. Okay, but we're looking into this third part now. So before we begin, let's see what we have seen so far. Okay, of course, we've talked about what Newton's universal law of gravitation is, and we talked about the formula. Remember that Newton's universal law of gravitation has two parts to it. Okay, it is directly proportional to something, and it is inversely proportional to something else. Okay, and then after that, we also saw the gravitational force between two static objects, okay, on Earth, okay, and on the Earth's surface, and then the Earth and the satellite, and also the Earth and the Sun. This is the thing that we saw in the last class. Okay, and then of course after that we also came up with a formula, okay, for gravitational acceleration, which is the small letter g. Okay, and how we determine that on Earth our gravitational acceleration is 9.81. Okay, but it's always good for us to know how they came about. How did they come up with this number 9.81? Okay, and we already proved that in the first lesson lah. Okay, and then in the second lesson, which was on Tuesday, we talked about the different planets in the solar system. Okay, and also one of the activities was to talk about the effects of different gravities on the human body. Okay, can the human body experience a very high gravity, or what happens to the human body when it experiences low gravity? For example, if we go to the moon, okay, what happens to our body? Or if we go to somewhere where the gravitational acceleration is higher, like let's say Jupiter, okay, what happens to our body? There are definitely changes that happen to our body, when we experience different gravitational accelerations. So we did that on Tuesday. Well, some of you did that on Tuesday, and I want to talk about this in a while later lah. Okay, so this was the formula that we talked about. Okay, F equals to G M1 M2 over R squared. Okay, and then the second one was this formula, which is G equals to G as in the gravitational constant, okay, times the mass of the Earth or the mass of the planet, okay, over the radius of the planet itself. Okay, whenever we talk about the gravitational acceleration, we always refer to the surface of the Earth, okay, because that's the standard R that we use lah. Okay, and we find that there was a relationship, okay, between G and the R. Okay, and if you remember the graph, it was directly proportional first. Okay, and then at the maximum over here, this is the gravitational acceleration on the surface of the Earth, and then after that, it will decrease. Okay, it will be inversely proportional. The further you are away from the surface of the Earth, the smaller the gravitational acceleration will be. Okay, you still have a gravitational acceleration, except that you'll get smaller and smaller the further you are away from the Earth. Okay, until a certain point where you can't feel the gravitational pull anymore. Okay, so that's the that's the that's the thing that we studied the first class. Okay, and then in the second class, I asked you to fill in this table. Okay, to find out the different gravitational accelerations in different planets in our solar system. Okay, and I believe that Pluto wasn't in our list. Okay, because actually Pluto is no longer considered a planet in our solar system. Okay, in case you didn't know that, but it's always good to know lah. Okay, since we've learned a little bit about Pluto in the last time. I mean, last time when you were much younger lah. Okay, but we find out that the planet that has the biggest gravitational acceleration, which is Jupiter, is about 24.8. It's about 3 times more than Earth, or 2.5 times more than Earth lah. Okay, and this is caused by a couple of things. Number one, of course, the mass of Jupiter is very big. Okay, it's a huge planet. It's the hugest planet in our solar system. Okay, and also the radius is pretty small. Okay, so we find that when the mass is big, okay, the gravitational acceleration also will be bigger. Okay, and we find that actually even though sometimes the radius is very big, contohnya like the sun lah. Okay, you find that the radius is very big compared to the Earth. And we know that from the formula, if the radius is very big, then the gravitational acceleration should be very small. But in actual fact, we find that another very big contributing factor is actually the mass. Okay, the mass, whenever we look at gravitational acceleration, we look at the mass lah. Okay, we find that the mass has a bigger impact, okay, rather than the radius itself. Okay, but it is undeniable that the factors that determine the value of gravitational acceleration are both the mass and the radius of the planet. Okay, we find that Pluto, the radius is the mass is so tiny. Okay, it's so much smaller compared to Earth. Earth is 5.97 times 10^24, but Pluto is 0.015 times 10^24. It's even smaller than our moon. Okay, so you find that in Pluto, which is the planet that is no longer a planet, okay, the gravitational acceleration is very, very small. So, if you make one jump, you will probably jump very high and very far. Okay, as opposed to if you're on Mercury, if you try to jump on if you try to jump on Jupiter, if you try to jump on Jupiter or try to do a long jump on Jupiter, okay, you probably won't travel very far. Okay, because the gravitational acceleration is so high that you try to jump on the gravitational field, okay, will immediately try to pull you down towards the surface of Jupiter. Okay, so it's pretty difficult. Right, so today we come to this last two parts okay, of this first subtopic, which is firstly to talk about this concept which is called the centripetal force. Okay, I repeat, the word is centripetal force. So if you notice that actually when we have satellites moving around the Earth, okay, it can be satellites, it can even be our moon, okay, it's always good to wonder how actually do they keep moving lah. Okay, and actually if you think about it, satellites and moons, okay, they actually move around very naturally. There's nothing driving them. As in, there's no internal engine there's somebody driving the satellite so that it always stays in a circle. No, actually it is not. Okay, we find out that when the satellites move, or even when when the sun moves around the Earth, or when the Earth moves around the sun, okay, it is actually drawn by a force, okay, or it's actually caused by a force that is called the centripetal force. Okay, so a body moves in a circular motion. Always experiences a change in direction, okay, of motion, even though the speed is constant. Now, in our last chapter, we talked about this. The speed may be the same, okay, because speed is a scalar quantity. But the change in direction is because, it's traveling around. So it is not traveling in a linear direction. Okay, any circular motion, any circular motion is always a change in direction. Okay, you change 1 degree angle, kau sudah tukar arah. Okay, so a change in direction, even though the speed is constant, is also known as a change in velocity. Okay, and if you remember our formula for change in velocity, change in velocity actually equals to rate of change of velocity actually equals to acceleration. So whenever there's a change of velocity, there must be an acceleration. Okay, and if there's an acceleration, then we can use this F equals to ma, okay, which we will come to in a while. So since there is a change in velocity, means there is an acceleration. If there's an acceleration, there's going to be a force that is acting on this satellite or the moon. Okay, so this force, okay, is known as a centripetal force. Okay, and this is the definition for centripetal force lah. The force that acts on the body which moves in a circular motion. Okay, that means dia berpusatkan kepada something in the center and then it's moving around it. Okay, any force that is moving in a circular motion, okay, or berdasarkan or based on a certain point in the center, okay, is the force that is moving this thing is called a centripetal force. So this is the force that is responsible for making sure that the satellite changes direction in a circular motion. Okay, if there is no centripetal force, okay, if there's no centripetal force, it means that when the satellite is traveling, it can just go straight. It can go anywhere at any time. But because there is a force that is pulling it towards the center, okay, and we know that the force is caused by the gravitational pull on the Earth. Okay, there is a what we call a gravitational field strength over here. There's gravity that's happening over here. Okay, so other gravity means there's other tarikan ke arah sini, but at the same time, our satellite also wants to move this way. Okay, so the combined forces together will cause it to go in a circle. Okay, so it's a combination of two forces. Sorry, it's a combination of two forces lah. One is the force of the satellite that wants to go in one direction, and the other one is the force of the gravitational pull from the Earth. Okay, that causes it to go in a circular motion. Okay, so to demonstrate this, I don't know if you have seen this, but actually in our textbook, there's this augmented reality app that you can download. But anyway, I already downloaded and I want to show this to you. Okay.
Bodies such as satellites and planets.
Okay, so you find that
in a circular motion when.
Okay, so you find that this is how the centripetal force works lah. Okay, the satellite goes around and around this one, and it is not being driven. There's no engine that is driving it. We don't have to constantly fill up petrol into the satellite, okay, in order for it to move around and around. Okay, so we find that what causes the circular motion of satellites or the moon around the Earth or the Earth around the sun is this force that is called the centripetal force. It is a new thing that we are learning. Okay, it is a new thing that we're learning. So let's slowly explore this. Okay, take a look again. The movement is circular. Okay, and it is actually being centered on the center of the Earth. If we draw a line, a perpendicular line from the satellite to the sun, you find that there's a certain distance, okay, between the satellite and the center of the Earth, which makes the satellite able to orbit at a certain height from the Earth. Okay. All right. So next one. Oh, sorry. Okay, so in order for us to get a better understanding of how centripetal force is like, okay, I want to suggest that you, and actually this is not a suggestion, this is definitely an assignment, okay. So I want you to try to do this centripetal force experiment in your own home, and actually you can substitute all these things for other things, okay. Let me give you a small adjustment suggestion. Okay, so for example, you have this plastic tube over here. Okay, I would suggest that you take a pen. Okay, you take a pen and then you open the back, and all I want is just this. Okay, all I want is just the body of the pen. Hold on. Okay, all I want is just the body of the pen. Okay, and if you take a look at the textbook, okay, when you use the body of the pen, then you can substitute that as the plastic tube. Okay, then you take a piece of string. Okay, it can be any string now. We've done this with raffia string. Raffia string not so good, but we've done this with thread, benang. Okay, kami sudah pernah pakai benang. If you have a thicker string, then it's a good idea to use thicker string. But if not, then you can always use benang. Okay, or even raffia string. Raffia string also can, but it may not be able to fit in here. Okay, so you put a raffia string over here. Okay, and After that, on one end, instead of a rubber stopper, okay, what you can do is you can use a heavy object like plasticine or tennis ball or something that's heavy lah. Okay, that you can tie it around. Okay, and then over here instead of the crocodile clip, you can use the yang sipit kain itu. The sipit kain lah. Okay, you can use the sipit kain. The purpose of the crocodile clip is to make sure that it always stays at the bottom of this. Okay, and then instead of the slotted weights, this slotted weights actually is only available in our lab, but you can substitute this for something else. Okay, what we did last time was we substituted this with a bottle of water. Okay, and the point is this now. So you hold the plastic tube in your right hand like this. Okay, and the slotted weights in your left hand. Then you rotate the rubber stopper at a constant speed in a horizontal circle above your head. Okay, and hopefully the rubber stopper doesn't hit your head lah. Okay, but the thing is this, you make sure that the crocodile clip stays at a distance of about 1 cm from the lower end of the plastic tube so that the radius is fixed. Because if the crocodile clip naik atas naik turun bahkan, that means this radius sentiasa berubah-ubah. We don't want that lah. Okay, you need to turn it in such a way so that the crocodile clip stays in place. Does it have to be 1 cm from the lower end of the plastic tube? Not necessarily. Actually, what we did last time was we made sure that the clip always stays there. Okay, it doesn't turun and yeah. But actually, better to be 1 cm lah. But if you can't, okay, you can always make it stay there. Okay, and you see the point of this is to feel how the centripetal force is like. Okay, so this pen or this slotted weight okay, actually acts as the earth. Okay, the earth with its gravitational pull. Okay, which is and this rubber stopper actually acts as the satellite that is moving around the earth, and the string, the pull on the string, okay, that you feel when the rubber stopper makes a circular motion, the stretched spring exerts a force. This string needs to be stretched, okay, in order for it to go around. Okay, so that force is what we call the centripetal force. Okay, it is the force that that is being pulled by the Earth. Okay, in order to make our satellites, our moon, to go around the Earth. Okay, yeah, I can talk about this now, but but actually it is best if you do it yourself, and you can actually do it at home. This is a home activity. Actually, you don't even have to go to the lab to do this. So this will be definitely an assignment. I want you to do this in your own home. Okay, you can totally substitute this. You can use, like I said, my suggestion, take a pen. Okay, just take the plastic tube. Sorry, take the tube or the pen, and you can actually do it already. All you need is a string, 2 heavy objects, or actually 1 heavy and 1 not so heavy, and the crocodile clip. Okay, so when we did this last time, when I was doing this, so these are some examples that you can refer to lah. Okay, so here's one. This is done by our master teacher. So this is what he did. Okay, so if you notice, actually he uses a water bottle. Okay, and then over here is actually a piece of plasticine, but it can be something heavy lah. But the point is to spin the whole thing, okay, so that the crocodile clip doesn't move about. Okay, and that's the aim of this. Okay, to get a constant centripetal force. Okay, so you need to move this thing around. Let me show you another example. This is 2 teachers from Tawau. Actually, one is from Tawau and the other one is from Sampurna. So this is what they did. Okay, so you notice that some people they use short string. His string is a lot shorter lah. Okay, so his string is a lot shorter than hers. Hers is very long. Okay, but the idea is the same: to move the thing around, as horizontally as you can. Okay, if you notice, actually this man, his movement is not so horizontal. Okay, yeah, it takes a while to get this correct. Okay, so when you move it horizontally, okay, as I said, the thing that is moving is actually representing the satellite, okay, or the moon that is going around the Earth. Okay, and this pull over here is representing the pull the gravitational pull that the Earth has on the satellite. Okay, and so this string over here that you see, okay, this string over here that you see, uh, okay, over here, okay, this string over here, there is a pull over here which we call the centripetal force. Okay, because in order for the plasticine to go around in a circular direction, it needs to be pulled towards a center. Okay, so that force that pulls it towards the center, in order for it to make sure that it goes in a circular direction, is called a centripetal force. Okay, so the word centripetal, okay, centripetal comes from two words in Latin. Okay, centrum means center, and petere or petere, okay, means to seek. It means that it is, it is seeking to go towards the center. That's why it's called a centripetal force. Okay, and let me repeat the definition again. The definition is the centripetal force is a force that acts on a body, which is a satellite or the moon, in a direction towards the center of the circle for a body in circular motion. Okay, so the important thing for centripetal force is the object must be moving in a circular motion. Dia mesti bergerak dalam satu bentuk bulatan. Okay, if it is going straight, then it's no longer called a centripetal force. Okay, and this is the force that causes all the satellites around the Earth, okay, to be able to move on their own, okay, to be able to orbit on their own. The word orbit, okay, is a very important word that we need to understand. Okay, they are not driven by an engine. They are not driven by a car. They don't have to keep refilling petrol because they are relying solely on the gravitational pull on the Earth. Okay, to help them to continue moving. And of course, this also is in line with our concept of inertia. Remember when we talk about inertia, if something is moving, it will continue moving unless there's an external force. Okay, so something that is moving in a circular motion will just continue moving. Okay, because the gravitational pull is always there. Okay, for it to change the direction. How do you change the direction of the satellite? Well, I can think of many ways. One is maybe you could bang it if maybe if it bangs with an asteroid, or if it bangs with another satellite, or suddenly our Earth loses its gravitational pull. All those things can cause the centripetal force to be to be less, or can cause our satellite to go somewhere else. Okay, but that's not our discussion today. Okay, our discussion today focuses on centripetal force itself. Okay, so I hope these two videos are helpful. I've already posted these two videos on your Flipgrid assignment, so you can take a look and see how it can be done. Okay, it can be done in a myriad of ways. Okay, figure out how to substitute. Okay, right. Okay, so the formula for centripetal force, okay, is F. Oh, sorry. Okay, is F equals to mv squared over r. Okay, mass times the linear speed v squared over r. Okay, what I want to mention over here is the radius of the circle is not the radius of the Earth. Okay, so this thing is very important here. The r is calculated from the center of the Earth to the center of the object. The radius is determined as the distance between the center of the Earth all the way to the object itself. That's the r that we talk about in this particular formula. Okay, so for example, in our situation over here, the radius is from here all the way to here. Okay, this is r. Whenever we talk about centripetal force. Okay, so previously we've always been talking about the radius as this is the radius of the Earth lah. Okay, I'm going to label it as RE. But when we talk about centripetal force, we need to remember that it is a force between two objects. Okay, the Earth and the satellite or the planet lah. So when we consider the radius, okay, we consider the distance between the center of the Earth and the center of the satellite itself. Okay, so please take note of this R over here. Okay, so there are three factors that affect the centripetal force. Okay, number one is the mass of the object. The bigger the mass, okay, if the mass is bigger, we find that the centripetal force also will be bigger. Okay. Secondly is your linear speed. If your linear speed is bigger, okay, then your centripetal force also will be bigger. Thirdly is the radius of the circle. If you take a look, hold on. Yeah. Okay, if you take a look at the radius of the circle, since the radius is is inversely proportional to the f, we find that the bigger your radius, okay, the smaller your centripetal force, which makes sense lah. You know, if your satellite is further and further away from the Earth, okay, then it's going to have less pull. Remember, we said that the further you are away from the Earth, the less gravitational acceleration you feel. Okay, so because of that, the centripetal force also will be much lesser. So we find that generally, the further you are away from the Earth, the slower your satellite moves. Okay, generally lah. Okay, so this is the answers for that I told you all to do, which is in the yeah. Okay, which is in this one, the 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 module that I gave you very early on. Okay, so I hope that you've done this. Okay, I'm just going to show this to you, and then later on you can rewind this video and you can copy it down again. But there are three factors that affect the centripetal force. Okay, and all the factors are shown in the formula itself. Okay, the formula is mv squared over r. Okay, and this relationship is very important to remember lah. Okay, so here is an example of a centripetal force in action, and this one we've seen before. Okay, I don't know, I can't remember what this event is called. Okay, but this is an athlete that's swinging an iron ball in a horizontal circle before releasing it. So we find that the centripetal force is acting this way. Okay, this is there. He is as if he is the Earth, and this iron ball is as if he's the satellite that is moving around. Okay, so we can actually find, or we can actually calculate the centripetal force. Okay, if we know how much is the speed of the ball. Remember, okay, the speed is always the same, but the velocity is different because velocity is a vector quantity. So since the direction changes, so the velocity also will change. Okay, so we use the information given, mv squared over r. Okay, and we find that the centripetal force, the force that is being exerted on this one to make it go around, okay, is 1,600 newtons. Okay, the formula is pretty simple to use. Okay, it's just the understanding of how the formula works. Okay, and because centripetal force is a new thing to us, not just to you, but also to us teachers. Okay, so I find this subtopic actually very interesting. Okay, because it explains a lot on how how the moon moves around the Earth and how the satellite moves around our Earth. Yeah. Okay, how the satellite moves around the Earth. Okay, and there are lots of satellites out there. Okay, and how they manage to gather enough force in order for it to continue to just orbit around the Earth without falling or or without something bad happening to it. It's an interesting thing to me. All right. But now, since we're talking about centripetal force, we also have to talk about Newton's interesting prediction. So Isaac Newton, our good friend from the first subtopic, okay, he predicted that the satellite can orbit around the Earth without being driven by a rocket engine. Okay, but there is a certain syarat, there is a condition. Okay, so if let's say you launch a satellite from a certain height. Okay, so the object launched from P with a linear speed of V. Okay, so if you launch it with a low speed, okay, a low linear speed, okay, what will happen is the gravitational pull will be very big, okay, towards it. So it will fall towards Q like that. Okay, but if you launch it at a sufficiently high linear speed, okay, that means the speed of launching must be high enough, okay, then it will be able to be following this second trajectory and it will continue to circle the Earth. Okay, it won't return to the Earth. Okay, so the question is, how much is the speed that is required? Okay, in order for it, so that the satellite, I mean, this is a fail case scenario. You launch a satellite, but it falls back to the Earth. Like, what? Okay, so you want to launch a satellite and it continues to go around and you don't have to worry about the satellite already. I mean, you don't have to worry about Okay, is the satellite going to fall? Does it have enough? Don't need. Because the centripetal force is the one that makes it go around and around and around and around. Okay, but in order for you to make sure that it has enough centripetal force, okay, you need to have a certain centripetal acceleration. Okay, and when you know how much acceleration it needs to reach, then you will know how much speed, okay, you need to launch it with. And this sufficiently high linear speed is something that we will calculate in the third subtopic. Okay, we will cover this in the third subtopic. But how do you know how much speed a certain satellite needs? Okay, in order for it, so that it doesn't fall into the ground. Okay, so that it will not return to the earth. Okay, but the first thing we need to know from here is how to calculate the centripetal acceleration. Okay, if we combine Newton's second law, which is F equals to ma, and the centripetal force that we got from the formula just now, we'll find that actually our acceleration, or otherwise known as the centripetal acceleration, is equals to v squared over r. Okay, so when we know, okay, how much the acceleration is, okay, then we can know how much speed we need to launch this one, okay, so that it will continue to go around. Okay, so I just made a point here. A change in velocity results in an acceleration. Okay, so there's definitely going to be an acceleration because there's a change of velocity. Okay, remember the speed is the same, but the velocity is different. I don't know how many times I've said this again. Okay, the velocity is different because the direction changes. And because there's a change of velocity, there is going to be an acceleration. Okay, so, and this is the thing that anybody who wants to launch a satellite has to make sure that you calculate it correctly. Because building a satellite, number one, costs a lot of money. Okay, building a satellite costs a lot of money. So when you want to launch it, when you want to launch it with the correct speed so that it can go on in its trajectory. Trajectory is dia punya laluan. Okay, if you don't understand what is the word trajectory, go and look up in the dictionary. Okay, but basically a trajectory is dia punya flight path lah. Okay, dia punya laluan, dia punya path of jalan, path of jalan. Okay, so already building a satellite is very costly. Okay, when you launch it, you want to make sure that you launch it and then it can go around by itself. It doesn't have to fall back to the earth, because falling back to the earth, okay, this is not like falling from your bed to the floor, guys. This is a big fall, and a big fall is going to cause the satellite to be rose up, okay, which is costing a lot of money, which is why the calculations for this have to be very precise. Okay, so how to calculate the high linear speed? We will talk about this in the third section, in the third subtopic. Okay, but this is another AR that was shown, that is actually available in your textbook. Okay, so we find that if you launch it at a low speed, okay,
from a high position will fall back to the earth.
Okay, so that, if you can't hear the voice, that is the person saying that, Newton is saying that if you launch a satellite from a high position but at a low speed, it may orbit the Earth, okay, for a while, but because the speed is not high enough in order for it to, achieve that centripetal acceleration, in order for it to get that centripetal force, it will fall back to the Earth.
According to Newton, objects that are launched at a low speed from a high position will fall back to the Earth.
Okay, so you find that even though it is able to, orbit the Earth, but because the speed is not high enough, okay, the linear speed that is being launched is not high enough, so the gravitational acceleration will pull it slowly down back to the Earth, which makes the satellite a failure, okay, which is what we don't want. So in order for the satellite to move around, okay, in a circular motion without being driven by the engine, it needs to be launched at a very high speed. Okay, and as I said, how much is the high speed? We will calculate in the third section. Oh, sorry. Okay, so this is the second page of your module. Okay, and this is the answer. So this is an example. Okay, and what we've been talking about before, the planets orbiting around the sun also experience a centripetal force. Okay, the force is pulling it towards the sun, but because the Earth is orbiting, okay, so it's able to move in a circle. Okay, in the same way, when you go through a loop on a roller coaster, okay, the wheel over here, okay, the center of the loop of the roller coaster, okay, you know, there is a centripetal force that is acting towards the center of the loop. Okay, even though the roller coaster is going that way, there is going to be a centripetal force. Okay, so we find that these are two other applications of centripetal force which we see in our daily lives. Actually, if you think about it, centripetal force is actually all around us. Um, think about our washing machine. Okay, you know when our washing machine, when we spin, right? Have you ever wondered now how come our clothes now all move to the side? You know, yeah. So that is also a possible explanation, you know, of centripetal force. Okay, so this is an example that is in our textbook, okay, of how to calculate the centripetal acceleration. I want to just remind you again that the r, okay, the radius that we're talking about here is not the radius of the Earth only, but it is the distance between the center of the Earth to the satellite, which is why they add both together. They add the radius of the Earth plus the height of the satellite. Okay, so in order for it to calculate the centripetal acceleration. Okay, v square over r, v is given 7.62 times 10 to the power of 3. Okay, and then the r, as I said, needs to be calculated radius of the Earth plus the height. Okay, we've seen this before when we were calculating the gravitational acceleration. Okay, just want to mention this once again. Okay, now we come to this last part. Now that we know, okay, the centripetal force, okay, or the formula for centripetal force. So we have these two very big formulas, okay, that Newton proposes to us. Number one is, oh, sorry. Number one is this. Number one is Newton's universal law of gravitation. F equals to gmm over r squared. Secondly, we also know that anything that is being pulled, okay, experiences a centripetal force. Okay, anything that is moving in circular motion that is being pulled towards the center experiences a centripetal force, which is F equals to mv squared over r. Okay, if we equate both of them, okay, and we simplify them, we get this formula, which is gm over r equals to v squared. Okay, and then if we replace v with this formula 2 pi r over t. Okay, so how do we get 2 pi r over t? Is this. So the distance traveled by the moon, okay, for example, the moon, okay, the distance traveled by the moon when it is making one complete orbit, okay, lintasan ini, if you think about it, is known as the lilitan bulatan, the circumference of the circle. So this is 2 pi r. Okay, so this is 2 pi r. Okay, because it is moving one whole circle. So the circumference of the circle is 2 pi r. And if you know how long it takes to travel, so 2 pi r over t, okay, is also known as the velocity of the moon or the linear speed of the moon. Okay, because remember, speed equals to displacement, speed equals the distance over the time. The distance of a circle is the circumference. The time, okay, is the time taken to travel one whole circle. So we can actually calculate the velocity of the moon. Same thing, we can also calculate the velocity of the Earth that is going around the moon. We just have to know what is the radius. Okay, the distance between the moon and the Earth, or the Earth and the sun, or any satellite and the Earth. Okay, so when we calculate the speed, okay, and we substitute it in here, okay, we find that it is gm over r equals to 2 pi r over t squared. Okay, and when we pindah, we can actually calculate the mass of the Earth. Okay, we can calculate the mass of the Earth by substituting all this. Okay, the r, as I said before, the r refers to the distance between the Earth and the moon. Okay, not the radius of the Earth. And the t squared, okay, is how long it takes, okay, for the moon to orbit around the Earth. Okay, so this is the answer for the third part of your this one. And we find that this is the formula on how to determine the mass of anything. Okay, the mass of the Earth, the mass of the Sun, the mass of any planet. Okay, and this is how we do it calculatively. It's not like we took a weighing machine to the planet and then, okay, Jupiter, please stand on the weighing machine so that we know it's not done that way. Okay, we have to manually calculate it. But there are two things that you need. Okay, for example, there are two things that you need in order for you to calculate the mass of the Earth. Number one, you need to know the radius between the Earth and any, and any satellite or the moon. Sorry, this is not off, this is or. Okay, the radius of the orbit, okay, around the moon, or of the moon or of any satellite. And the second one, you need to know how long it took them to go one whole round. How long it took them to go one whole round is known as the period of revolution. Okay, masa untuk satu pusingan lengkap lah. Okay, satu putaran lengkap. Not putaran, satu pusingan lengkap. Okay, one pusingan lengkap is called the period, how long it takes. So when you have these two information, pi is a set information, 22/7, 3.142. G, since the last time you already know, is 6.67 times 10 to the power of -11. So that one doesn't change. But when you have these two, okay, if you want to calculate the mass of the Earth, you need to find something that is orbiting around the Earth. Okay, and get the R and get the T, then you can calculate the mass of the Earth. Likewise, if you want to calculate the mass of the Sun, you need to know the radius of the orbit of any planet. Okay, that means, let's say we choose the Earth, so we need to know the distance between Earth and the Sun. Okay, the radius between the Earth and the Sun, we need to know. Secondly, how long does it take for our planet to revolve around the Sun? And this one we know. It takes us 365 and a quarter days to revolve around the Sun. Okay, 365.25 days to revolve around the Sun. Okay, so this information is given here. The period of the, let's go to the Sun first. So the Earth revolves the Sun in a period of 1 year. Okay, and the radius of the orbit R is 1.5 times 10 to the power 11. That means the distance between the Earth and the Sun is about 1.5 times 10 to the power 11 meters. Okay, so we can use this to calculate the mass of the Sun. So 4 pi squared times the R cube, okay, times G, and then where did we get this 315360000 from? Okay, because we need to change this into seconds. Into seconds. Okay, so 1 year, let's break it down. 1 year is 356 days. Okay, 1 day is 24 hours. Okay, 1 hour is 60 minutes and 1 minute is 60 seconds. Okay, wow. It's 3075840. Okay, later we will fix this lah. It's actually 3075800. Okay, but we will get the mass of the Sun is about that 2.10, 2 times 10 to the power of 30 kilograms. Okay, which is much higher than the Earth. Okay, so remember, if you want to find the mass of a certain planet, of a certain moon, okay, of the Earth, you need to find something that is orbiting around the planet or the Earth or the Sun. Okay, and then, only then, okay, can you find out, and then after that, you need to find out how long it takes for it to move one whole circle, okay, which we call the period of revolution. Once you have those two pieces of information, then you can calculate the mass of any planet. Okay, so as this is a bonus thing which you don't have to do, but if you want to do, it's also good information to find out. It's actually possible for you to use this formula, okay, to calculate the mass of the other planets in the solar system. Okay, if you want to know this, you're more than welcome to do some research, because at your level, okay, you're only required to know what is the mass Okay, but it's interesting to find out how did they calculate the mass of the Mars, or how did they calculate the mass of Uranus, or how did they calculate the mass of Saturn. Okay, but they use the basic same formula, but there's a slightly different way Okay, in how they would know okay, how to do that. Okay, so please remember that we use these two formulas plus this formula 2 pi r over t to terbitkan okay, to come up with the formula for the mass of the sun. Okay, this chapter is especially slightly difficult because there's a lot of terbitan. Okay, you have to from this f. Okay, from this f, you need to know how to terbitkan the small g. Okay, and then after that, you use these two to terbitkan this mass of the earth, mass of the sun, punya formula. Okay, so how to terbitkan this formula is a very important thing. So let me remind you once again, okay, that this module, okay, this module that I gave to you, uh, this module that I gave to you, whenever you see something that you need to terbitkan, terbitkan means I don't know what is it in English lah. Okay, derive. Okay, whenever you have to derive a formula, for example, how do we derive the gravitational acceleration formula? This one is very important. Okay, as physics students, you need to know how this is derived. Okay, is it going to be tested? I'm sure it's going to be tested because it is in your syllabus. You are required to know how it is derived. Okay, so be very careful with this stuff. So far we have two derivations. Three derivations. Okay, we have three things that you need to derive, and all three also you have to remember. Okay, so am I done? Are we done? Okay, so so this thing is a bonus thing now. If you want to know how to calculate the mass of the other planets in the solar system, you can always find out more. But I mean, if this is already like wow, it is a lot. Okay, this last part of this subtopic is actually a little bit difficult because there's a lot of calculation and there's a new thing that is involved, which is the meaning of the centripetal force. Okay, so take some time. It's okay. Take some time to let it sink in. Okay, but actually it is not as difficult as you think it is lah. Okay, it actually makes a lot of sense. Okay, we see centripetal force around us every day. Okay, it's just that we never think about it because so far everything we've been talking about is left, right, or up and down. Okay, so now it's time for us to think in a circular motion. And higher level physics actually deals with this lah. Okay, whenever things move in a circle, there are other things to consider. Okay, so this is a good introduction to the world of circular motion. Okay, but for your homework today, I want you to do a Flipgrid assignment, okay, showing the centripetal force activity. Okay, the one like this one lah. Okay, so use materials from your own home. Okay, use materials from your own home. If you want to be very berani and use this, no lah, don't lah. Okay, so use materials from your own home to substitute. Okay, you can use water bottle, like in this case, this guy used water bottle, pen, and a plasticine. Okay, there is no clip buaya, but actually it's better if you have a clip buaya lah. Okay, but definitely all of you will need to do this as a solo Flipgrid assignment. Okay, so when you read the instructions in the Flipgrid lah, okay, I already said that once you do this, when you demonstrate this, also answer these three questions. Okay, use the demonstration to answer the three questions. Okay, then your second assignment or your second homework is actually, I've already posted this up in your Google Classroom, page 95, questions 1 to 6. Okay, please submit this before next Tuesday. The Flipgrid video, actually, you can take your time because I want you to concentrate on your PBL first. Okay, ini PBL mesti jalan dulu because your PBL is a very important thing lah. Okay, I cannot stress this more than enough. Your PBL is a very important thing. Okay, so take your time to do this centripetal force activity, but preferably before Hari Raya, I want this centripetal force activity to be done. Actually, this one kan setengah hari pun cukup ini. Okay, you probably only need 2 hours to complete this, but it's okay. Okay, figure out the PBL first. All right, so I see that we have a couple of questions from some people. So, okay, so hi Cikgu Wan Rahima. Okay, so she asked, Is it all the value students must remember, or is it given? I suppose that most of the values will be given. For example, the mass of the Earth. The mass of the Earth definitely is given now. But actually, you need to know how to calculate it also. Okay, so let's say for example, this one. Okay, so the period of revolution around the moon, has to be given. Okay, because you're not required to design. But the mass of the Earth, okay, if you're asked to calculate the mass of the Earth, then you will need this information. Definitely, you will be given because these are constant. Okay, these are constant, so they will definitely be given. Okay, so I don't think you have to memorize them now. What you should be memorizing is what does the R and the T mean. I think that's a very important thing that you should be memorizing. Okay, remember R is the radius between the two objects, not the radius of of the Earth or the radius of the Moon. Because previously, whenever we talk about F equals to this one, right, the R always refers to the distance between the two objects. Okay, so we don't change it from there. The maybe confusing part about this, and I admit it is a confusion, is that sometimes R refers to the radius, as in the jejari bumi, or the radius of the Earth or the radius of the Sun, and sometimes R refers to the distance between two objects. Okay, so if it helps lah, okay, if it helps, I think that if you take a look at this, okay, this whenever we talk about force, okay, whether it is Newton's universal law of gravitation, the gravitational force, or the centripetal force, the R always refers to the distance between the two objects. Okay, the distance between the Earth, the center of the Earth, and the center of the Moon. Okay, that's the R. But when we talk about gravitational acceleration, sorry. Okay, when we talk about gravitational acceleration, okay, this one depends on where your object is. Okay, if your object is on Earth, okay, then the R will be the radius of the Earth. But if the object is, like a satellite that is above the Earth, then the R will still be the distance between the object and the center of the Earth. Okay, so I think it's just a matter of getting used to these formulas, okay, that we see from time to time. Okay, thank you for the question. Is there any more questions for anybody? Okay, while waiting for the question, I also want to address my own students. There are a couple of things that I need to mention. Number one, I want to remind you that for those of you who have not completed your nearport lesson, okay, this lesson will close tomorrow. Okay, because some of you, what you did is you submitted an empty table. So I'm like, what am I supposed to do with this empty table, people? Am I supposed to give you a big fat zero? Okay, so please complete your nearport lesson for those of you who haven't completed it. Okay, so this is one that you need to do. You need to fill in this table and submit it properly. Okay, take a look at how Irdina does it. Okay, this is so much more easier for me to this one. So please don't submit empty things like this. Okay, in the future, also please do not do that. Secondly, I gave you an assignment also to talk about the effects of gravity, high gravity and low gravity on the human body. Okay, and I divided you all into different aspects, and I told you all to hand in the collaborate board. Okay, so if you take a look at the collaborate board, hold on, waiting. Okay, if you take a look at the collaborate board, okay, if you take a look at the collaborate board, the number of people that send in their collaboration is actually very few. I can actually count them with two hands. Valerisa, Rania, Angeline, Isabella, Tien, Jacinta, Daniel, Irdina, and Michelle. That's it. Okay, so for the rest of you who haven't done this part, okay, I really want to make sure that you complete this part. So for those of you who haven't done this lesson, please do this lesson after this after this class. Okay, because this is a ini wajib lah. Okay, so as I see, okay, Lester and Jericho already done. Okay, good for you. Okay, but for the rest of you who haven't done, please complete these 2 lessons. Okay, before the lesson closes. Tomorrow, sorry, by tonight, the lesson will officially close. Okay, then after that, what happens will be what happens lah. Okay, so if there's no questions, thank you for your attention, okay, for today. And please complete your homework, okay, and then I will see you in the next lesson. Okay, take care everyone. Bye.